Welcome to Unit 8, Lesson 3, Solving Exponential Equations. So an exponential equation, we've been talking about it already. It's an equation that has a variable in the exponent. So these equations, they can be written in different ways, and typically they're going to end up having a different base number than you need to solve it. And what you need to think about is what are the roots, what number multiplies together multiple times to give you the base number that you're provided with. So an example here, 4 to the power of 2x is equal to 8 to the power of x plus 1. Now, we are trying to solve for x. That hasn't changed. So what we need to do is change 4 and 8 to the same base. And then once we're able to do that, we can set the exponents equal to each other. So 4 to the power of 2x. 4 is 2 squared to the power of 2x. And then 8 is 2 times 2 times 2, or 2 to the power of 3, to the power of x plus 1. So notice that nothing happens to the exponents yet. They get left alone. You need to change your bases first and then work with your exponents. Once we've done that, we can use that general formula. I'll just go back to the first page of the first lesson. You have these general formulas here to help you. Now, the one that we're working with here, 2 to the power of 2 times 2x, we can use multiplication. So it's this example here, a to the power of m times n. We're just going to go m times n. Okay. So 2 to the power of 2 times 2 is 4, and x is left over. In the right-hand side, you're going to use the distributive property. Don't forget to multiply the 3 by both terms. It's kind of like you have this if we were just dealing with only the exponent, 3 times x plus 1. So you're going to distribute the 3 through that whole bracket, 3 times x and 3 times 1. So you'll get 3x plus 3. Now that our exponents are equal to each other, because we have the same base function, we can just eliminate the base and just solve for x using the exponent. So we say 4x is equal to 3x plus 3. And you might be saying, like, why are we doing that? That doesn't make any sense. This is the reason why. If we have an equal sign in our equation, we need to get to the end result that the left-hand side is equal to the right-hand side. So that means that whatever the value of x is, this side, this exponent, and this exponent need to give us the same 2 to the power of whatever exponent at the end. So we say 4x is equal to 3x plus 3, and then we solve for it by moving the 3x to the left-hand side, minus 3x from both sides. You're just left with x, and then 3 on the right-hand side. We have x equals 3. You can check to make sure that you've done it properly. So your left-hand side, if you resolve this equation, should equal your right-hand side. I'll just quickly do that here. 2 to the power of 4 times 3 is equal to 2 to the power of 3 times 3 plus 3. This gives us 2 to the power of 12 is equal to 2 to the power of 3 times 3 is 9, plus another 3, 2 to the power of 12. You can just punch this into your calculator. You're going to look for one of two buttons. It's either going to be a hat button like that to the power of, or you might have a y to the x button, whatever that looks like on your calculator. So you can solve this. I don't know what 2 to the power of 12 is, but if you just punch it in your calculator, you can get the result. However, if you're just solving for x, you know that you've done this properly because both left and right side are equal to each other. Just like we were doing in the previous example, we want to just be able to look for the powers of the expression that we're given. So you might have to add some brackets into your solution here, but it just says rewrite each expression as a power with a base of 3. So you don't actually need to resolve the equation here, you can just leave it as an exponent. So 27 is equal to 3 to the power of 3, which of course is 3 times 3 times 3. 9 squared. Now it says a base of 3. So you want to look at the 9 and say, oh, what value of 3 times 3 will give us 9? Of course, it's 3 squared. Notice that that squared equation stays the same there for the exponent. So we have 3 to the power of 2 times the power of 2, or 3 to the power of 4. This one looks a little bit crazy, but just do it step by step. So 27, of course, we just solved it over here, is 3 to the power of 3, the power of 1/3. And then 81 is 3 to the power of 4. This one equals 81, by the way. So 81 is 3 to the power of 4 cube root squared. So you've done and resolved the problem for exactly what it's asked you to do. You can always simplify it further and punch it into your calculator if it asks you to actually solve for it. In the next two examples, we're just taking the base and changing them into a common base so that we can solve for x. So on the left-hand side, 64, we need to figure out what base of that gives us 4. So we have 4 here, 4 to the power of x plus 2. 64 is 4 times 4 times 4, or 4 to the power of 3 to the power of x. And then you just simplify it out and solve for x. So 4 to the power of x plus 2 is equal to 4 to the power of 3x. And then just eliminate that base. X plus 2 is equal to 3x. And at the end of it, 1 equals x. The same thing on this side. You end up with a fraction 9 over 2, but this one is very similar to the first example, so I'm not going to go completely through that. Now you can go on and check your solution by just plugging back in the value of x into your formula and making sure that your left-hand side equals your right-hand side. If it does, then you will have done the problem correctly. You may also be asked to do application problems, so solve problems involving exponential equations with different bases. I should preface this little part of the unit and say that sometimes you won't be able to just use straight math to be able to solve a problem. And in this circumstance, with this example, guess and check is okay. That's a valid mathematical practice to kind of say, I think it might be this, plug in a value and try it, and then see if you need to go higher or lower. In the next unit, we're going to talk about how to solve this using our calculators and not have to guess and check. But for this part, you can just go ahead and solve it this way. Okay. At the top there, I put in some terms for financing just so that you're aware. You know, when you go to the bank and get a loan, they'll say, oh, the interest is compounded annually or biweekly, or however they're going to charge you the interest on the loan that you take out. These are the terms. So these are the numbers that you would use. For annually, it's just 1, semi-annually 2, quarterly 4, monthly 12, biweekly 26, and weekly 52. It just corresponds to how many payments you're making per year. So the example, Christine plans to buy a car. She has saved $5,000. The car she wants costs $5,900. How long will Christine have to invest her money in a term deposit that pays 6.12% per year? If you can get an investment that pays you 6%, you should put your money in there. Compounded quarterly before she has enough money to buy the car. So we have this compound interest formula. It's A, which stands for the amount that you're looking to make, is equal to P, the principal, that's how much money you're investing, times 1 plus I, that's your interest rate, to the power of N. And N is the number of compounding periods, or how many times they pay out the interest per year. So in her loan, the interest is at 6.12%, and it's paid quarterly, so 4 times per year. That's the only number that you're actually going to have to do something with. So you'll just take the interest rate as a decimal. Don't forget to change it to a decimal. Divide by 4, and you'll get the decimal point 0.0153. Once you've done that, you can substitute your known values into the equation and then solve for it. So what we've done here, we've kind of isolated away the variables to leave us with this final term. So we've divided both sides by 5,000. That's where the 1.18 comes from. And then in the brackets, we've just added these numbers together, 1 plus 0.0153 to the power of n, and that will give us the right-hand term here. Now, these are not some clean numbers where you can very easily see what the exponent would be. So what we're going to do in this part is we're just going to use guess and check to see how long it will take her to make this money back. So let's start with 10 payments. There's no rhyme or reason why I picked 10. It's the one I started with because we need somewhere to start. So 1.0153 to the power of 10, that equals 1.1639, etc. on your calculator, which is less than 1.18. So don't forget we had on the left-hand side 1.18. That's our goal. We're trying to make it match up to that value. So that was too low. Let's try a higher number. So we try 14. That gives us 1.24, which is greater than 1.18. So that would mean that we took too long to gain our money back. So we know that that value of n will fall somewhere between 10 and 14. 1.16 was pretty close to 1.18. So try 11 next. Just be systematic about it so that you're not jumping all over the place. So you plug that 11 in, and it gives you approximately equal to 1.18. It's 1.817. So with rounding, it's 1.18 equals 1.18. That tells you that the number of compounding periods is approximately 11. So since the interest is paid quarterly, there are 4 compounding periods per year, and therefore it'll take 11 over 4 or 2 3/4 years for Christina's investment to reach a value of $5,900. Probably in this circumstance, you would want to just save that extra $900, but this is an example of how that compound interest builds up over time. That's why when we talk about investments, we say, oh, put the most amount of money in early so that when you're leaving your investment sitting there, it builds up that interest faster and you get a better return on your investment. Beyond this, you have some practice questions that you can complete on this topic.